Welcome to the video lecture series for Texas A&M University course Math 150. Today we will look at section 2.6 Rational Functions. You can find the accompanying handouts at bit.ly/RayleneMath150. Let's begin. A rational function is a fraction or a quotient of two polynomials. This is not a surprise when we see the word ratio or fraction inside the name. So we have a fraction of two polynomials where the degree of the denominator polynomial is greater than 0. Let's explain what that means in part B. A rational function must have a variable in the denominator. So for example, y equal to x squared plus 1 over 5 is not a rational function because 5 is a constant polynomial with degree of 0. Because that is the exponent on x. So in other words, we must have at least a linear function in the denominator for the rational function to be considered a rational function. In the case of y equals x squared plus 1 over 5, this is nothing more than a quadratic function. Part C takes another look at the definition of a rational function. It says that a rational function has the algebraic form of f of x, the rational function, equal to the ratio of the numerator n of x over the denominator d of x. So n of x is a numerator polynomial, and d of x is the denominator polynomial. The division algorithm says that the quotient n of x over d of x can be written in the form of quotient plus remainder over denominator. Let's just remind ourselves of this. When we see 7 divided by 3, we've got numerator over denominator, and it can be written as 3 goes into 7 2 times plus 1 over 3, which is quotient plus remainder over denominator. Just as an extra concern or consideration, the 1 is the remainder is not 1/3. So q of x is the quotient polynomial, and r of x is the remainder polynomial. Notice that if q of x is equal to 0, then n of x over d of x is equal to r of x over d of x. So the numerators, since the denominators are the same, the numerators n of x and r of x would be equal whenever the quotient is 0. The equation forms for a rational function, well, just like for linear and quadratic functions, we have different ways of expressing a rational function. The linear function had point-slope form, slope-intercept form, and intercept form, while the quadratic equation forms were intercept form or factored form, the vertex form or transformational form, and the function form. So the three forms for a rational function are, first of all, proper form. If the degree of the numerator is, if a fraction is to be proper, the degree of the numerator is to be less than the degree of the denominator. And in that case, we get the quotient is 0, and again, the numerator is directly equal to the remainder. This is proper fraction form. The numerator and denominator may be further expanded or factored. For the improper fraction form, the degree of the numerator is greater than or equal to the degree of the denominator. So I'll just write in words, greater than or equal to the degree of the denominator. And in that case, f of x equal to n of x over d of x can be divided using long or synthetic division as q of x plus r of x over d of x, where once we've divided properly, r of x over dx will be in proper fraction form, meaning that the degree of r is less than the degree of d of x. The numerator and denominator may be expanded or factored in this form as well. Transformational form, well, as always, if we know the graph of the parent function, we can apply transformations to it to sketch a transformed graph. Transformational form is always a factored form. Let's take a look at the graph of y equals x minus 4 over 2x plus 1 and put it into transformational form. Well, in this case, we need to get the quotient, so I'm going to divide 2x plus 1 into x minus 4. When we do this long division, we ask ourselves, how many times does 2x go into x? In other words, x over 2x is equal to 1/2. The 1/2 is a constant, so I'm going to line it up in my constant column. When we multiply back through, 1/2 times 2x is x, and 1/2 times 1 is 1/2. Now subtracting, we see x minus x is 0x, and if this doesn't happen when you do the long division, you have made a mistake here, or distributing back through. And then -4 minus 1/2 is -4 1/2 or -9/2. So we see we have a remainder of -9/2. So what this means is that we can rewrite the fraction in this form as y equals 1/2 plus the remainder -9/2 over the denominator 2x plus 1. We see that the 1/2 is really being a transformation of vertical translation to y, and then we have -9/2 being multiplied by 1 over 2x plus 1. This vertical reflection in scale can be written on the other side as -2/9 times y minus 1/2, and we can really see this as 1 over 2 times x plus 1/2, and the 2 could be separated as 1/2 times 1 over x plus 1/2, so we could again see another scaling factor. We could either leave it there with the x, or we can take it to the y side. Since we already have a vertical scale, and this 1/2 can be separated as follows: 1/2 times 1 over x plus 1/2. I'd prefer not to have both a horizontal scale and a vertical scale. So if I double both sides of the equation, this will disappear from here, leaving me without a horizontal scale. So if I double the right-hand side, I'm left with 1 over x plus 1/2. And if I double the left-hand side, I have -4 over 9 times y minus 1/2. So in this case, I have a parent function of y equals 1 over x. I have a vertical reflection, a vertical scale of 9 over 4, a horizontal translation of -1/2, and a vertical translation of +1/2. This may seem like an awful lot of work to get the transformations, or it may seem like a lot of transformations. In this video, we are going to see alternative methods to graphing rational functions than from using transformational form. It will involve a sign chart. Here are two common parent functions then, as we just saw, 1 over x, and of course the reciprocal square function, 1 over x squared. If we complete the table of values, the reciprocal of -10 is -1/10 or -0.1. The reciprocal of -1 is -1. The reciprocal of 0 is either -infinity or +infinity. For example, as x approaches 0 from the left-hand side, y approaches -infinity. So we could say that the reciprocal of 0 is -infinity. However, x can approach 0 from the right-hand side, in which case the reciprocal has to be positive as well, because the reciprocal does not change the sign. As x approaches 0 from the right, y approaches +infinity. And so it's a little unclear in this case to say what the reciprocal of 0 is. It's either -infinity or +infinity, depending on the side of the graph that x approaches 0 from. So I'll just indicate plus or minus infinity for this graph. When x is +1, the reciprocal is 1. The reciprocal of 2 is 1/2 or 0.5. The reciprocal of, I'll write it as a decimal just so we can see the trend. The reciprocal of 10 is 1/10 or 0.1. The reciprocal of 100 is 0.01. As x increases towards infinity, the reciprocal of these values approaches 0. Over here, when x is -10, the reciprocal square is going to be 0.01. The reciprocal square of -1 is +1. And let's do the other non-zero values for now. The reciprocal square of 1 is 1, of 2 is 4, of 10 is 100, and of 100 is 10,000. Going back to 0, as x approaches 0 from the left-hand side, we see that y approaches +infinity. Yet as x approaches 0 from the right-hand side, there's no change in y. And this, of course, happens because of even symmetry. So in this case, we get y approaches only positive infinity. We can see that from a sign chart point of view, x squared is positive and the reciprocal does not change the sign. Let's take a look at two rational functions that don't have vertical asymptotes but still have discontinuities. The almost constant function, or the basic removable discontinuity, is y equal to x over x. Of course, we can rewrite this as y equal to 1 as long as x is not equal to 0. So no matter what x is, as long as it's not 0, y will be 1. And when x is 0, y is 0 over 0, which is indeterminate. And in this case, because x is approaching 0 from the left, means that y approaches 1. Meanwhile, as x approaches 0 from the right, y approaches a height of 1. We can see that the left-hand limit is 1, the right-hand limit is 1, and so we have a hole in the graph as opposed to a jump discontinuity. And that hole in the graph occurs when x is 0. In other words, we have a hole at the x-coordinate that made y indeterminate. In the case of the step function, we know that we can replace the absolute value of x with either negative x or positive x, depending on whether x was less than 0 or greater than or equal to 0. And then taking negative x divided by x, we would get negative 1, as long as x is not 0, so less than 0. And when x is greater than or equal to 0, we replace absolute value of x with x, so that becomes x over x, which is 1, for x positive but not equal to 0, because we would get indeterminate. And so in this case we have the y-coordinates as follows, and we have 0 over 0, which is indeterminate when x is 0. The difference with the almost constant or removable discontinuity case is, as x approaches 0 from the left, y approaches a height of negative 1, while as x approaches 0 from the right values, y approaches a height of positive 1. These two values are different, so the left limit is finite, the right limit is finite, but they are different, and therefore we have a jump. So our graph looks like this. And the jump discontinuity comes in from the fact that we have different left-hand limit and right-hand limit behavior. Again, the left-hand limit says as x approaches 0 from the left, y is approaching a height of negative 1. And as x approaches 0 from the right, y approaches a height of positive 1. Because negative 1 does not equal positive 1, the left-hand limit does not equal the right-hand limit. Meanwhile, over here, as x approaches 0 from the left, y approaches a height of 1. As x approaches 0 from the right, y approaches a height of positive 1. The left-hand limit and the right-hand limits are the same. So let's just write that in here. I'm going to write that the left-hand limit equals 1, the right-hand limit should be left-hand limit, and the right-hand limit equals 1, the left-hand limit equals the right-hand limit, and therefore the limit as x approaches 0 of x over x equals the same value that the two one-sided limits was equal to. Meanwhile, over here, the left-hand limit can be expressed as the limit as x approaches 0 from the left on the graph of absolute value of x over x, and that height is negative 1. The right-hand limit can be expressed as the limit as x approaches 0 from the right on the graph of absolute value of x over x, and the height that y approaches is positive 1. And we say that because the left-hand limit does not equal the right-hand limit, that the overall limit, or simply the limit as x approaches 0 of absolute value of x over x, does not exist. And we write does not exist as a backwards capital E with a slash through it. So we're talking about rational functions, which are ratios of polynomial functions. And what's the same about what we've seen from functions before? Well, the functions that we've seen in the previous sections of our text are mainly polynomial functions: constant, linear, quadratic, cubic. Of course, we've seen other power functions, like the square root of x or the cube root of x, which are the inverses of x squared once we restrict the domain of x squared, and the inverse of x cubed. But for the most part, we've been dealing with the polynomial functions, or polynomial piecewise functions, like absolute value. So the things that's from before are the X-intercepts. We know that any X value that makes Y defined to be 0 is an X-intercept. There could be no X-intercepts in the case of a quadratic not intersecting the X-axis, which we said meant the discriminant was negative or less than 0 from the quadratic formula. There could be one X-intercept or more than one X-intercept depending on the shape of the graph. For Y-intercept, we still have Y-intercepts for rational functions, which is the value of Y, or the Y value that makes X 0. But we don't always have a Y-intercept, it depends on the graph. Okay, so let's move on. What's new about rational functions? Well, for the first time we are introducing a variable in the denominator. And as a result, we have the domain restriction that denominators cannot be 0. And every time the denominator might equal 0, it could lead to a discontinuity. The three discontinuities are vertical asymptote, or infinite discontinuity, which is an X value that makes Y undefined, or we could have a removable discontinuity or hole, or we could have a jump discontinuity. So if we take a look at finite X values, we have domain restrictions and discontinuities. Denominators can't be 0, so we can use that fact to determine the domain of any function, any rational function. But we do that before factoring and reducing, because the factors of the denominator will be in the original unreduced function. The three kinds of discontinuities we just talked about, just briefly, they are holes, jumps, and vertical asymptotes. For a hole, we said just recently with the x over x graph, which is our basic removable discontinuity function, we were saying that the graph of f has a hole in it at x equal to a whenever the limit value exists but does not equal the function value. So we could have a graph like this, or we could have a graph like this. In the red case, we have a limit value as x approaches a. Let's say that the hole here is at a comma b. So we would say that the height of the hole is the y-coordinate b. But we would also say that f of a does not exist. It's not defined to be anything. In the blue case, we might still have the hole located at a comma b, but we might have a y-coordinate or function value defined at a different height from b. Let's call that height c. In this case, we would have the limit as x approaches a of f of x is b, but f of a is equal to c. Either way, whether we do have a function value or we don't have a function value, if it's not the same as the limit value, the function is not continuous, and we have a removable discontinuity. The next case is to look at a jump. A jump in the graph of f occurs whenever the finite height that y approaches from the left is different from the finite height that y approaches from the right. So let's take a look at the absolute value of x over x graph. We saw that in that case, as x approaches 0 from the right, y is approaching a height of positive 1, and as x approaches 0 from the left, y is approaching a height of negative 1. These two heights are finite. They are not plus or minus infinity, but they are different. And so we have that the limit as x approaches 0 from the left of absolute value of x over x is equal to negative 1, but that value is not equal to the right-hand limit as x approaches 0 from the right of absolute value of x over x, or on the graph of absolute value of x over x, whose height is 1. And therefore, we would say that the limit as x approaches 0 of f of x, or absolute value of x over x, does not exist. It's possible that we could have defined a y-coordinate, let's say at 0, 2. So we could say, in this case, that f of 0 is equal to 2. But still, the limit value does not equal the function value, and so the function is not continuous. Whenever the left limit is different from the right limit, although both of those values are finite, we have a jump discontinuity. The word finite is important here because it's possible that we could have, let me just draw the graph here, it's possible that we could be looking at y equals 1 over x, or 1 over x squared. In this case, if we're looking at the reciprocal square function, we have even symmetry, And we could say that as x approaches 0 from the right, y approaches a height of positive infinity. And as x approaches 0 from the left, y approaches a height of positive infinity. So one could argue that positive infinity from the left and positive infinity from the right are the same heights, and therefore the limit exists. But the limit must be a finite height or a finite value, because otherwise there is no limit to what that height can be. All right, the third type of discontinuity is a vertical asymptote, or infinite discontinuity. And a vertical asymptote occurs whenever a finite x value makes y undefined, so non-zero over 0. So this means that no y value satisfies the equation, for example, 0y equal to, if we were to say that non-zero number is 3, then 0 times y is equal to 3. We remember that this said no solution. We sketch the vertical asymptote as a dotted vertical line at x equal to b. So depending on whether we have a vertical asymptote with odd behavior, like x to the 1 here, or a vertical asymptote with even behavior, like y equals 1 over x squared, we may have the left and the right hand limits being the same or different. On the 1 over x to the 1 case, as x approaches 0 from the left, y approaches negative infinity. But as x approaches 0 from the right, y approaches positive infinity. So the left-hand limits are different, and they are infinite. That's really, really bad behavior for the limit. The limit definitely does not exist. Meanwhile, in the even behavior case of the vertical asymptote, as x approaches 0 from the left, y approaches positive infinity, and as x approaches 0 from the right, y approaches positive infinity. Like I just mentioned in the previous slide, even though y is approaching the same height, that height is infinite, and therefore the limit doesn't exist. The long story made short is whenever an x value, such as a, implies that y is approaching positive infinity or negative infinity, that's the undefined case, and therefore we have a vertical asymptote at x equal to, well, here I've called it b. I'll call it b. We have a vertical asymptote at x equal to b. Never, ever, ever will a function cross the vertical asymptote. You can read this bit here on your own, just pause it, and recognize that we're talking about the definition of a function. If we are going to cross a vertical asymptote, then we would be violating the definition of a function for that to happen. The short story is, functions do not cross vertical asymptotes ever. All right, something else that's new for rational functions that we've never really seen before. Well, actually that's not true. We've seen end behavior, but we've never called it the non-vertical asymptote. So in a sense it's new. We've looked at polynomials like y equals negative x cubed plus 2x squared minus 5x plus 8, which has end behavior of like y equals negative x cubed, which is the parent function of x cubed vertically reflected. We have looked at the end behavior. In other words, what does the graph look like when we zoom out? But we've never had to deal with the quotient and the remainder of the denominator from polynomials before. Because there is no denominator, there is no quotient. So in the case of rational functions, if we look at infinite x values as x approaches negative infinity or as x approaches positive infinity, we are no longer looking at discontinuities. We are looking at end behavior, and another way to refer to end behavior is the zoomed out behavior. Okay, the end behavior means the behavior of y, the height of the graph, at the left and right ends of the graph. So the left end is x approaching negative infinity, and the right end is x approaching positive infinity. The end behavior indicates what height the y values approach as we zoom out on the graph. So algebraically, we would write this on the left end by saying the limit as x approaches negative infinity of f of x, and on the right, we would write the limit as x approaches positive infinity of f of x. And we've seen this already in the functional analysis that we've performed on a few of the basic or parent functions. A special case of end behavior, or zoomed out behavior, or non-vertical asymptote behavior, and I'm clarifying vertical versus non-vertical because vertical asymptotes are types of discontinuities, infinite discontinuities, whereas non-vertical asymptotes are not discontinuities. They do not come from domain restrictions. What the non-vertical asymptote is what the graph looks like when you zoom out, but it is not a discontinuity. So the special case of a non-vertical asymptote, or non-VA, is if the left end behavior equals the right end behavior, and that is a constant, then we are saying that y approaches a constant height when we zoom out. If we let that constant be k, what we're saying is that the function has a horizontal asymptote, because y approaches a constant. That's a horizontal line. And the equation of that horizontal asymptote is y equal to k. For any proper fraction, and we remember that a proper fraction has the degree of the numerator smaller than the degree of the denominator. If this fraction is proper, then the limit as x approaches plus or minus infinity of r of x over d of x is equal to 0. The reason for this is simple. Let's take a look at, well, the reason isn't simple, but we've seen it before. Let's take a look at y equals 1 over x. This is already a proper fraction, so we could call this numerator over denominator, but we could also say that this is quotient plus remainder over denominator, where the quotient is 0. And as we stated earlier in the lecture, as we said that the quotient of x is 0, the numerator is the same as the remainder. Well, if that's the case, if we look at the limit as x approaches infinity of the proper fraction 1 over x, as x gets bigger, 1 over bigger approaches 0. So whenever we have a proper fraction, the numerator grows slower than the denominator. If the denominator is bigger than the numerator and getting bigger and bigger and bigger towards infinity, then the reciprocal of infinity is 0. All right, continuing on. The non-vertical asymptote is the shape that the rational function looks like when we zoom out on the graph. The equation of the non-vertical asymptote is y equals q of x. The question is why? Well, let's take a look at these two graphs, and I'll draw them again on the graphing program. If we were to perform the long division, we would get that this numerator divided by this denominator gives us this quotient, a remainder of 1, and the same denominator. Oops, that should say of x squared, because it should be the same denominator. Actually, now that I look at it more closely, I think once we reduce the fraction, that wouldn't happen. We would get x outside of 1 minus x squared all over x squared, and we can reduce the fraction here to get 1 minus x squared divided by x, which could be written 1 over x minus x squared over x, and we see that x squared over x gives us the negative x squared over x gives us negative x plus 1 over x. So we indeed have the quotient of negative x. So let's look at the graph in a different window. We have y equals x minus x cubed divided by x squared. Okay, if we zoom out, eventually this graph looks like a slanted line. And the slanted line that it looks like is the quotient that we get when we divide the numerator by the denominator. That quotient is negative x. If we zoom in, we can eventually see that the two graphs don't look the same. So they're not the same functions, but they have the same end behavior. They have the same zoomed out behavior. And how we get that is by looking at the quotient. So anytime we want to get the equation for the non-vertical asymptote, we do that by putting the improper fraction into proper fraction form and looking at the quotient. Okay, so the different types of non-vertical asymptotes really depend on the kind of polynomial that q of x is. If q of x is a constant, then we would say that we have the non-vertical asymptote is a horizontal asymptote. If q of x is equal to a linear function, then we would say that we have a slant or oblique non-vertical asymptote, so a slant asymptote. Asymptote is just the end behavior shape or model or function. If we had the quotient, q of x, is a quadratic function, then we would say that we have a parabolic asymptote. Again, just to be clear, the horizontal asymptote, the slant asymptote, the parabolic asymptote, these are not types of discontinuities. So they are different in behavior from a vertical asymptote, which is a type of discontinuity coming from a domain restriction. These asymptotes are what the graph looks like when we zoom out far enough. And each graph has a unique non-vertical asymptote. If we take a look at y equals, let's say x cubed minus 1 divided by x plus 2, we see that the denominator has a 0 when x is negative 2, and sure enough that gives us a vertical asymptote. And if we continue to zoom out, it becomes harder and harder to see, so I'm going to change the range a little bit, maybe go from negative 10 to 10 for x, and negative, let's say 1,000 to 10,000 for y. And if we zoom out now, we see that the graph looks like a parabola. Let me change the range a little bit. Instead of 10,000, let's make it 1,000. And so we can still see that different behavior, but we zoom out, eventually we can see we don't even need to go very far. X doesn't really need to approach infinity or negative infinity for us to see the end behavior or parabolic asymptote shape. We're only going to x is 200, 300, 400. That's not very close to infinity. So depending on what shape the end behavior is, you may or may not have to zoom out very much to see the end behavior. It's not a mystery that this is going to be a parabola, because when we take the leading term of the numerator, which is x cubed, divided by the leading term of the denominator, which is x, we can predict the quotient will be x squared over x cubed over x will be a quadratic. To get the full equation of the quadratic, ax squared plus bx plus c, and not just the leading term, we would have to do long division or synthetic division to get the full quotient. Okay, so unlike vertical asymptotes, let's just contrast non-vertical asymptotes. They are not a kind of discontinuity. The non-vertical asymptotes represent the zoomed out behavior of the function. They have nothing to do with denominator or domain restrictions. Also, non-vertical asymptotes sometimes do get crossed by the rational function. Let's keep in mind that the rational function is y equals f of x, which is a numerator over a denominator polynomials, equal to the quotient polynomial plus remainder over denominator. Again, that's like 7 over 3 is an improper fraction, which we put into proper fraction form. So this is proper fraction form here. We put it into proper fraction form by saying 3 goes into 7 2 times, plus a remainder of 1 over the denominator of 3. 2 would be the quotient, 1 would be the remainder, and 3 would be the denominator again, same denominator, and 7, of course, is the numerator. Well, what we're saying is here we have a function f of x. We know that the quotient is the non-vertical asymptote. We want to know, do they intersect? So we solve the system. We look for intersection points. If this is a red function here, and the quotient function, or non-vertical asymptote, is drawn in green, we want the red height to equal the green height. So we solve for red y equal to green y. In other words, we say that f of x, which is equal to this improper fraction form, or this proper fraction form, so q of x plus r of x over d of x is the original function, would be equal to the green function, which is the quotient. We notice that the quotient is the same function on both sides, so they subtract and give us 0, and then we're left with r of x over d of x equal to 0. We know from our work with defined, undefined, and indeterminate values that the only way for a fraction to equal 0 is if the numerator equals 0. We also know this because we could clear the fraction by multiplying by the LCD, not cross-multiply, and that would give us the statement that says r of x is equal to d of x times 0, which is 0. So the only way for the fraction to equal 0 is if the numerator of that fraction is 0. In other words, the only way for the non-vertical asymptote to be crossed by the rational function is if the remainder term has a root. So this either has a root or a solution, a real solution, therefore intersection point or points, or no solution, no real solution, and therefore the function does not cross or intersect its non-vertical asymptote. Okay, we'll see some examples of these. I want to outline a few steps for graphing and analyzing rational functions. We're putting a lot of the pieces that we've been doing over the past several weeks together into one problem. And being good at this is really the basis of understanding a lot of the calculus that we will see in Math 151. When we want to graph and analyze rational functions, the first thing to do is to fully factor and reduce the improper form and state the domain restrictions. Then express the reduced equation in proper fraction form. Get coordinates of any holes, get coordinates of any X-intercepts, get vertical asymptote equations, perform the sign chart using the roots of the reduced numerator and denominator, just like we've been doing sign charts in week 5. Then we get the coordinates of the Y-intercept. There will only be one Y-intercept by definition of a function, although there may be more than one X-intercept, but only one X-intercept if the function is one-to-one. Then we get the equation and state the type of non-vertical asymptote. We see if the function crosses the non-vertical asymptote, and we sketch the graph. Don't forget to use symmetry if possible. So let's take a look at an example putting all of these into play. I'm going to skip number 1. We've done it before. And I think maybe I'll start off with number 2 simply. So we're going to sketch y equals 3x minus 3 over x plus 2 as fully as possible using those steps in number 7. So we have y equals 3x minus 3 over x plus 2. And the first step says to fully factor and reduce the improper form. So this is improper because the degree of the top is 1 and the degree of the bottom is 1. So we can factor out a constant, but we don't have any common factors, and therefore we don't have any holes in the graph. So we are ready now to move on to the next step. Express the reduced equation in proper fraction form. So that's step 1. Step 2 says to perform the long division. So I'm going to do long or synthetic division. Negative 2 divides into 3, negative 3. You get negative 6, which is negative 9. And so I know, I'm just going to erase this here. So this is step 1. Step 2 says that I can rewrite this function as 3 minus 9 over x plus 2. Okay, the next step tells us to get the coordinates of any holes. Well, x coordinates of holes, to this we say none. And the reason is because there are no common factors to the top and the bottom before reducing. Because no common factors in numerator and denominator. The next thing we look for are the X-intercepts. We know that the X-intercepts are values of x that make y 0. And the only way for y, which is a fraction, to be 0 is if the numerator only is 0. And so this says that 3x minus 3 equals 0, which says that x equals 1. So we have an x-intercept at 1, 0. Okay, then the next step says to get vertical asymptote equations, and that was step number 5. So vertical asymptote equations, remembering that vertical asymptotes are values of x that make y undefined, which is non-zero over 0 for y. So the only way for y to be undefined is if the denominator only is equal to 0. So the denominator equal to 0 tells us that x plus 2 equals 0, and therefore we have a vertical asymptote at x equal to negative 2. I'm just going to write here that this is equivalent to saying to get an x-intercept is that the numerator only equals 0, whereas to get holes, both the numerator and the denominator would equal 0. Okay, so the denominator only equals 0, and now we're moving on to step 6, which is to take the zeros from the numerator of step 4, and to take the zeros of the denominator, which is step 5, and put them together to make a sign chart. So the sign chart has negative 2 for x, and positive 1 for x. The negative 2 is not included in the domain, so I'm going to exclude it with a dashed line and a circle, and the positive 1 is included in the domain, and in fact it produces an X-intercept, so I'm going to plot that along the x-axis already as an X-intercept of the graph. And then the factor that gave me negative 2 from our function was x plus 2, and we had x minus 1 for the factor that gave us the root x equal to 1. You can include the factor of 3, but since it's positive, it does not cause any vertical reflection or change of sign in each region. Then we know that one of these factors divided by the other is y, or f of x. Filling in the sign chart as quickly and efficiently as possible, we get the sign chart. It looks the same as if it had been a parabola, except of course we can't have a parabola because we have a domain restriction leading to a discontinuity. From here, we can continue to build our graph from the sign chart by introducing the y-axis. So let's go back up to the steps. The steps say, get the coordinates of the y-intercept and get the equation and state the type of the non-vertical asymptote. So we're moving into the y information. So I'm going to put the y-axis here at x equal to 0. I'm going to draw it longer than my other boundary lines. I have x equals negative 1 there. And I'm ready to do my shading. I know that the graph will lie above the x-axis for the first region, so I will shade below, then I shade above, then I shade below. And I'm going to clean up my sign chart so that I can draw the graph and the spaces remaining. So I want the y-intercept, which is the value of x when y is equal to 0. Sorry, the value of y when x is equal to 0. So if we set x equal to 0, we get from y equals 3x minus 3 over x plus 2, we get negative 3 over 2, which confirms our sign chart because y has to be negative in that region. Okay, so we plot our y-intercept. The next step says to get the equation of and type of the non-vertical asymptote. Well, the non-vertical asymptote is simply y equal to the quotient, and the quotient we found from the proper fraction form. So the proper fraction form, if you recall, was 3 minus 9 over x plus 2. This 3 is the quotient, and it is a constant. So in our non-vertical asymptote, we have y equal to 3, which is a horizontal line. So therefore the type is a horizontal asymptote, okay, or simply HA. So we can plot the horizontal asymptote as a dashed line. It doesn't have the same meaning as the dashed line for the vertical asymptote, which means a discontinuity. But we will still draw it as a dashed line because it's not part of the graph. I'm going to move this. And so at y equal to 1, we have a horizontal, y equal to 3, we have a horizontal line. 1, 2, 3, which is the horizontal asymptote. In other words, when we zoom out, the graph will look like a horizontal line if we zoom out far enough. The next step says to get the coordinates of any points where the function crosses its non-vertical asymptote. Well, we're looking to find intersection points of the system y equals 3x minus 3 over x plus 2, and the horizontal asymptote, which I'll put in red here. And the equation of that horizontal asymptote is y equal to 3. Remember, it is never possible for a function to cross a vertical asymptote, but a function may cross non-vertical asymptotes, and we're going to see now if that's true. We set the blue y equal to the red y, but we also know that the red y had a proper fraction form. This is improper. The proper fraction form was 3 minus 9 over x plus 2. So if we take this expression and set it equal to the red 3, we end up with 3 minus 9 over x plus 2 equal to 3. The 3's on the left and the right are the same, and we're ending up with a statement that says negative 9 over x plus 2 is equal to 0. And if we multiply by x plus 2 to clear the fraction, we end up with a statement that says negative 9 is equal to 0. Since this is false, we have no solution or no intersection points. What this tells us is that our function, when we draw the graph, will not cross or touch the horizontal asymptote. Well, at this point, we're ready to draw the graph. We've got nothing else to add to it, and it just takes a little bit of experience to know how it works. We have some information to know that the graph has to go through these points, and it will not cross the horizontal asymptote. So the graph is going to do something like this. Furthermore, it's going to come down, as x approaches -2 from the left, y is going to have to go towards -infinity because the region above the x-axis is blocked out. So the graph is going to do this. On the other side of the vertical asymptote, we need a branch of the graph. There's no way for the graph to be in here. We know that the graph will not cross the horizontal asymptote, and it has to run along the other side of the vertical asymptote, I should say, as x approaches -2, must make y go to positive infinity. So the other side of the graph, or the other branch of the rational function, has to be here. That's a bit hard to see, so I'm going to highlight my curve. And that's the best we can do without calculus to find the graph of a rational function. But the analysis that we are doing here from using precalculus methods is still pretty accurate. So really you need to try all of these steps one after the next on all of the practice problems. I will continue making videos for the remainder of the questions, but I will leave this video here so that you can practice on your own, take a break, and check your answers with me later. So please make sure that you have completed the handout and prepared a list of clarifying questions about the lecture. That's all for now.